Welcome to another Principles of Engineering video. This video is on work, energy, and power. All right, so let's start out with work. Work, oh, that's evil, four-letter word. We use the symbol W. Work is energy. This is the energy that we produce when we have a force and we apply it over a distance. When that force and that distance are in the same direction, they're parallel to each other, then we produce work. If they're at an angle to each other, that's going to diminish the amount of work that we do. And this is a dot product. If you're familiar with scalars and vectors, we've talked a little bit about them. We'll be talking more about them in upcoming videos. Work is not a vector. Work is a scalar product. Force, though, is a vector, and distance is also a vector. So we're taking two vectors, we're multiplying them together to get a scalar. And this is called the dot product. You notice it's got the little dot there. And if you're familiar with dot products from class, then you'll have a little bit more insight into how work works. We're going to be considering just the parallel case and not the case of forces and displacement at different angles for this video, that is. So work is done by the parallel force on our component. This is a very, very important concept. The symbol for work is W, of course, and the unit is the joule. Joule was a famous scientist that worked a lot in showing the relationship between thermal energy and mechanical energy, and we're going to kind of talk more about that later on in this video, about energy transfers. So he was very important in energy. And 1 joule is the equivalent of a Newton meter. If I have a Newton of mass and I push it 1 meter, I've done 1 joule of work. And now that mass has 1 joule of work energy stored in it. Can then maybe be used to reproduce that joule of energy back in another direction. So let's take a look at an example. Here a student has lifted a 50-pound ball, very muscular student, 4 feet in the air, and it took them 5 seconds to do it. So the question to you is, how many joules of work did the student complete? Pause the video and use the calculation on the previous slide to compute that work. Well, hopefully you gave that a try. The calculation would be work equals F dot D, and we have 50 pounds of force, and we have 4 feet of displacement or distance. Multiply that together, of course, you get 200 foot-pounds. Now, if you've watched the previous videos, you know that torque is also in foot-pounds. So is work and torque the same thing? No, they're not. As a matter of fact, torque is maximized when force and distance are at 90 degrees to each other, when they're perpendicular to each other. Work is not that case. Work is maximized when force and distance, or force and displacement, are parallel to each other. So that's one big difference. Another big difference is work is a scalar, torque is a vector. Another difference is work is energy, and torque is about the ability to make things spin. So work and torque are different concepts, but they do share the same units in the imperial system. So, but they don't in the metric system, or the SI, System International. So let's take a look at that. Let's convert that 50-pound ball and the 4 feet it moved into SI. So 50 pounds, well, 1 Newton is the same as 0.225 pounds. So there's our conversion factor. The pounds cancel, and we end up with 222.5 newtons. Also 4 feet, well, 1 meter and 3.28 feet are the same thing. So we can use that as a conversion factor and get 1.22 meters. So let's multiply those together. 222.5 newtons and 1.22 meters. And we get an answer of 271 joules. So 271 joules of energy were used to apply a force of 222.5 newtons to move that ball 1.22 meters. And now that ball has 271 joules more energy. If we lifted it straight up, it has 271 joules of potential energy. that could be maybe used for something else. We'll talk about potential energy in a few slides. So let's talk about energy in general. What is energy? We use this term all the time. Well, the ability to do work. Well, it's a good thing we defined work first. So we understand what work is now. Now we can think about the ability to do work, and that is energy. And there's lots of different forms of energy: light, heat, mechanical, chemical, electrical. These are all forms of energy and all used often and frequently. So, potential energy. I mentioned that a few slides ago. Potential energy has the capacity to do work by virtue of its position or its configuration. For example, let's say we have a handful of coal here, a handful of some other material that through chemical reaction could do work. It's not doing any work right now, but it could do work. All right? Could be a 50-gallon barrel of oil. All right? It could be a tank of gas, natural gas. They all, due to their internal makeup, have the ability to do work. But it also could be by position. A very, very common potential energy that we'll be talking about is gravitational potential energy. All right? If you lift an object away from the Earth's surface, you're going to be adding gravitational potential energy to that object. It's going to have more ability to do work the higher you lift it, or the more massive it is. There's also elastic energy. If you have a rubber band, not so much. But if you start to stretch it, you do work on it, right? You're applying a force, and that force is being applied over a distance, and that increases that rubber band's ability to have potential energy. It has more potential energy than it did before you started to stretch it. Electrical energy also, you might have a battery, and that battery has a voltage. It has the ability to do work, and if you create a circuit, work can be done. So let's take a look at kinetic energy. This is about motion. All right, when things are in motion, they have kinetic energy. So the movement of whole objects, this is usually the type meant by kinetic energy. Electrical energy can put electrons in motion, so it also has kinetic energy. Sometimes we use kinetic energy when we talk about thermal or heat energy because the molecules are moving around. They're moving, they're vibrating, and this internal energy can be also thought of as kinetic energy within that item. As it heats up, it has more internal energy or more kinetic energy. So energy doesn't just always stay the way it is. We transfer it. We've already alluded to this, right? Chemical energy can become kinetic. Radiant energy can become chemical. Electrical energy can become thermal and cook ourselves a nice turkey dinner. Renewable energy sources. Biomass, the use of living and once living organisms as fuel. Hydropower, the energy produced from the movement of water. Geothermal, the use of the heat from within the earth or from the atmosphere near oceans to warm houses and other buildings. Wind. We can use wind to generate electricity by turning turbines. Solar, the use of the sun as a source of heat, or on a photovoltaic cell, can get those electrons in motion by using the right combinations of semiconductors, producing electricity. Now, of course, there's non-renewable energy sources. And of course, these are the energy sources that we currently rely on the most. Coal, for example. We have to usually dig this up out of the ground. You can see this massive device for excavating coal. And you can see there's a little teeny person right there. This thing is huge. All right. We also get natural gas out of the ground, and that's used often to cook our food and also generate electricity. Petroleum is used, and uranium in nuclear power plants, also a source of energy. As it decays, as it produces fission, that heat that's released is energy. And we can use that energy, that heat, to generate electricity. So let's talk about the conservation of energy. There are, of course, in some of your classes, they've talked about conserving energy as, trying to make do with less. There's also is a very common meaning if they talk about conserving energy on the TV news, for example, or in middle school or elementary school classroom. Setting your thermostat to a colder temperature for heating in the winter and a warmer temperature for the air conditioner in the summer. These are all ways to conserve energy, maybe insulate your house more. But we want to talk about another way of saying conservation of energy, or another meaning for the conservation of energy, and that's the physics concept that energy cannot be created and it cannot be destroyed. It can only change from one form to another. So all the energy in the universe is the same today as it was yesterday, as it will be tomorrow. All right? It's the same. You go back a billion years, the amount of energy that exists then is the amount of energy that exists now. So that's the universe. Well, what about right here in our classrooms, in our houses, in our bedrooms, right? What about there? Well, in a closed system, if we can isolate the system and not have any forces in and out of that system, we can do calculations that show that the energy is being conserved. All right, so that's the first one. Second one, energy lost to heat. Well, so I say that energy can be changed from one form to another, but can't be destroyed. It turns out that when we do convert energy from one form to another, that much of our energy is converted to heat. And heat is not as valuable as other forms of energy. It's not as useful. There's heat all around us. All right, our body is producing heat. Our appliances are producing heat. The monitor in front of you is producing heat. Or if you're watching this on your phone is producing heat. You aren't doing anything to capture that heat. Maybe your hand's cold and you're trying to warm it up on your phone. Well, good for you. You're conserving energy. But overall, when our appliances produce heat, we just let that heat dissipate into the room. And if the room gets too hot, we open the door and we try and get that heat to go outside and go someplace else. So a lot of energy is lost to heat. This basically makes up the first and second laws of thermodynamics. When we do produce heat, like I said, if you can have a cold reservoir to draw that heat in, well, then that's going to be useful. You can maybe use that heat for something else. But normally that's not part of our system. I was lucky enough to visit the power generation station at San Jose State, where they use a jet turbine, right? This is a jet engine that could be on an airplane, and they use it to generate electricity. Well, it also generates a lot of heat. Well, during the day, they use that extra heat sometimes to melt ice that they made at night as a way of conserving that heat. They also use that heat to heat up water, to heat some of the buildings on campus. They're always trying ways to capture that heat. All right, so energy conversion. So here's several different examples of energy conversion. Fossil fuels, for example. The gas you put in your car, that is a chemical energy. But we use our engines, we use our cleverness inside our engines to convert that chemical energy into heat energy. That heat energy, of course, expands, which we turn into mechanical energy. And that mechanical energy could turn a generator. And that generator would make electricity. We also use solar cells. Solar cells can be used a couple different ways. You could heat up water, and that water could reach a boiling point, and that boiling water will expand and turn a generator, generate electricity. Or maybe it's a photovoltaic cell, and the chemical composition of that solar panel and the light energy from the sun work together to get the electrons in motion to create electricity. Okay, so energy conversion. Wind turbines. The wind blows, that's kinetic energy. It turns the turbine, turns the big windmill blades that turn the turbine, that turn the generator. This is mechanical energy that then generates electrical energy. Hydroelectric. If the water is uphill, right? So we've got a stream feeding a lake, and that lake is up in the mountains. We could put the dam at the base of it could have a hydroelectric generating plant. So the gravitational potential energy of all that water and the pressure of the depth of that water will then turn the turbines, right? That's mechanical energy, and those can be connected to electrical generators, making electricity. All right, we also talked about nuclear just a minute ago, how that can produce heat. That heat can lead to expansion, can lead to mechanical energy, which then, of course, turns a generator, making electrical energy. All right, so these are just a bunch of examples of energy conversions. So what about the chemical? When you convert chemical energy into mechanical, there's also heat. Which one is the most desirable? All right, I think I pretty much gave that away in a previous slide. So think about that. Now, efficiency. This is very, very important. There's lots of TV ads about efficiency, about Gold Star appliances, how efficient they are. And of course, they're talking about conserving energy. They're talking about the kind of efficiency where we're trying to accomplish the same result, cooling our house, cooling our food, but with less energy. That's the kind of efficiency they're talking about. And that's, of course, a very common meaning. We're taking it a little bit differently. We're looking at how much energy we get out in comparison to how much energy we put in. That is the efficiency that we're going to be calculating. So how do we calculate that? Well, efficiency, we're going to use a symbol. It looks like a little N right there, that little symbol. It's pronounced eta, E-T-A, eta. So the symbol eta is going to be used, and it's a percentage of the input energy that is transformed to the output energy in our system. So energy out divided by energy in times 100, that's eta. That's our efficiency. So what kind of efficiency do we see in the systems around us? Well, most electrical power plants and internal combustion engines have an efficiency around 30%. Yeah, not that great. Coal power plant, for example, only 30% of the energy from that coal is really going to end up as electricity. The rest of the energy goes out the smokestack as thermal energy in the flue gas. If the power plant is a co-generating power plant, then it can capture some of this energy maybe as another form of useful output. For example, heating a building. Then the efficiency can go up, maybe as high as 80%. Now in a car engine, also again, about 30%. 30% of the energy in that gasoline is actually going into the drivetrain to move you down the road. The rest, heat. There's also some sound energy there. You can hear the engine's noise and rumbling. Now we can, if on a cold day, turn on our heater and recover a little bit of that heat, warm us up inside, but eventually that heat will eventually dissipate out into the atmosphere and be gone forever. All right, so what are current energy concerns? Well, consumption, right? Are we using it up? Are we using it up faster than we can find new sources or replace them with renewable sources? There's also issues of pollution, dependency, right? Sometimes we get our energy from places in the world that aren't very dependable. Sometimes there's political turmoil that's caused by the energy that they're selling us. All right, that can cause problems for these people in other parts of the country. And of course, costs. All right, it's very expensive to keep your cars filled up. So what roles could engineers play in this? All right, do engineers have solutions? Can engineers produce solutions to these problems? All right, power. All right, the symbol for power is the capital P. This is the rate at which energy is expended or work is performed. Anytime you hear the word rate, you should think divide by time. All right, insurance rates. How much do you have to pay the insurance company per time? Hotel rates. How much do you have to pay for that hotel or per time? All right, per day probably, right? So rates. So power is energy divided by time, or in this case, work divided by time. So the SI unit for power is the watt. So that is also a capital W. So like what gives robot Riedinger? All right, how can we have a W here for watt and a W here for work? Well, this can cause a bit of confusion for a student, but think about it this way. This W for work, we're only going to see in formulas. And we should see it in formulas, right? Don't go skipping straight to the numbers. You should be writing down formulas, and you'll use the capital W for work in your formula. Whereas watt is a unit, not a symbol, but a unit. And units like watts, they go with numbers, right? So you're always going to see a number next to that W when it's watts. And you won't see a number next to this W when it's work. So types of power. Well, there's electrical power, mechanical power, fluid power. Mechanical power, we're used to that when we think about the size of our light bulbs, right? Mom might tell you, hey, go get a 40-watt bulb. Or now that they're compact fluorescents, maybe it's a 12-watt bulb. Mechanical power, when some motors are listed by their power, how many watts, all right? Or in the imperial system, how much horsepower do they have? You know, we have to compare it to something, so they compared it to a horse. Also, fluid power. How much power are we getting out of this fluid in our energy transfer? Could be hydraulics, right? Or it could be gases, pneumatics. So let's take our example of our student who is enjoying lifting that 50-pound ball over and over again. Remember, they lifted it 4 feet and they lifted it in 5 seconds. Well, we didn't do anything with that 5 seconds last time. Well, now it's important because we're calculating power. So how many watts of power did the student use to lift the ball? Well, we already established that the work was equal to 271 joules. All right, you can go back to that previous slide if you can't remember how we did that. Well, power is work divided by time. That's 271 joules divided by the 5 seconds it took the student to lift that ball 4 feet, a ball of 50 pounds. So that gives us 54.3 joules per second, or 54.3 watts. All right, thank you very much. I hope you learned a lot about work, energy, and power.